All right, happy Monday. Best day of the week. Brand new, fresh week. We either do something with it or we're going to waste it. Let's do something waste it. Yeah, let's do something with it. We're going to jump into atoms and molecules. I'm super excited about this chapter. We're trying to start chemistry. Kind of got through the background intro. We're going to kind of see some of the history of chemistry, which I think is pretty fascinating. My dad was a historian. Not in science, but in other things. So it's fun to, I do have a passion for seeing the history in certain things. Just some bookkeeping. CHE, I noticed there's 33 active people on a CHE. We have 34 in this class. If someone still doesn't have an active account, 3 people did not finish it last night. If that's one of you, I will give you one-time grace period. Send me an email, I'll open it back up for you. But 30 of you completed it, so that's good. That's good. That's pretty good for our first chapter. Usually I have a few more people that are outstanding. So good job. I did go back. I don't know if you got that. I wrote out problem 27 or whatever longhand. I hope that helped some of you. So if you got that email, great. If not, oh well. That said, anything else you want to go through or you want to jump in? You all good? Everything good? I can open that back up if you want that, but there was no point to it. So it was just the chapter that had points. Okay, yeah. So, all good? Ready? Ready to roll? Okay, I'm going to give you the big picture up front. I'm a big picture kind of guy. I like sort-ofs. I like itches. I'm not one of those concrete sequential type of people. I'm really random abstract, and it drives my wife crazy because she is very, very methodic in what she does, and I'm like, whatever. That said, I'm going to give you the big picture up front, and if those were to the wise, the heart and soul, and one of the most difficult things coming out of chapter 2 is something that we have to memorize. So some of you have already put time in the trenches and done this, great. If you have not, you have got to memorize these two tables. Okay, I will work through these tables on Wednesday or Friday with you and show you why and how. They're really cool. And they don't have to be just rote memorization, because there's a real logic as to how this happens. I'll just give it to you. This is Wednesday's lecture, not today. But this is a nitrate, a carbonate, a sulfate, a phosphate. Okay, they're going to add a bunch of oxygen. We get the polyatomic anion. So again, some of you had chemistry, kind of can already speak that language. We have nitrate, nitrite, carbonate, carbonite, sulfate, sulfite, phosphate, phosphite. This is NO3 minus. This is CO3 2 minus. This is SO4 2 minus. This is PO4 3 minus. There's a real rhythm as to why those polyatomic anions do what they do. But these are the cations, these are the anions, and these are typically the ones that are most difficult for students to memorize. I will walk you through why they're very systematic in what they do, but this is what you want to start working on. This is going to be the bulk and the majority coming out of this chapter is going to be working with speaking the language of chemistry. If I say aluminum hydrogen sulfate, you should know exactly what I'm talking about and know the structure of that. If I say magnesium acetate, copper dichromate, we need to speak the language of chemistry, okay? Then we'll look into binary nomenclature, what I call molecular nomenclature. Why is it when we combine a cation or a metal and a non-metal, different nomenclature than when we combine two non-metals? So we say something like dinitrogen trioxide. That's a very different nomenclature than with the cations and the anions. So that's what this chapter builds on. And here's why. Once we can speak the language, once we know the formula, now we can start to do reactions with those. So that's why this is a very foundational chapter in establishing the language of general chemistry. Make sense? So these two tables, the cations, very straightforward. They are just the metals. Most of them are just the metals. You just have to know their charge. +1, +2, +2 and 3, 2 and 3, 2 and 3, 2 and 3, 2 and 3, 1 and 2, 2. Wow. You just have to kind of memorize those. Okay, so again, I'll work through those when we get further along the chapter, but I'm going to give you the big picture up front. I typically see students struggle a little bit more with the polyatomic anions, and that's not all the ones. There's more that I'll add to that list. This is a partial list. Okay, good. Big picture right there. Boom. That's what really we want to take home out of this chapter. We want to be able to speak the language of general chemistry. Now, chemistry, of course, is the study of matter. And it does matter because we use chemistry all through what we do, whether it's cooking, whether it's medicine, whether it's technology, whether it's just discovery itself. Chemistry is a very robust discipline. Like I introduced it in the first lecture, it's the central science for a reason. It stands centered between biology and physics. So it is that central science. Now, that said, it's been around. Philosophers for literally for a long time have been trying to figure out what is the really real. All right, what is really real? What is all of this made out of, and how can we discover what it's made up of? And so we've made some progress in that. Do we know it all? Absolutely not. There's so many things that we still don't have a clue what's going on out there. But we have made a lot of strides since the first use of the word atom and void by Democritus. And looks like David Coverdale. And Isaac Newton proposed a mechanism, the universe, that's small, solid masses in motion. That's pretty revolutionary for 1704. This tiny little world in motion. Today, of course, we know that the nucleus has the proton and the neutron, or at least we still believe, because we use the Bohr theory of it. It's still just a theory, it could change. I'll show you another theory, it's actually kind of cool too, it has nothing to do with Bohr theory. But there's just the theory that the nucleus contains the protons and the neutrons, and there's little weird things buzzing around out there called electrons. But again, it's these little solid masses in motion. So how is it that we came to our understanding of what the atom is today? How is it that we believe that the nucleus contains the neutron, the proton, and the electrons in these things called quantum states? One of the persons that worked on this at a real fundamental level, very, very intelligent and hardworking scientist by the name of John Dalton. He is the one that really talked about the atoms being the fundamental building blocks. As we move into our nuclear chapter, we'll see that the protons and the neutrons are actually made up of smaller particles. Okay? We call them quarks, we call them leptons, bosons, fermions, and all these little mini particles. And we'll see some of those, how they all come together and how they all kind of make up the neutrons and the protons. And so really that these little fundamental building blocks was put forth by John Dalton. And so Dalton did some really amazing postulates. He actually thought through, okay, if these things are these little building blocks, there's a couple things that must probably be consistent. Didn't know these, but he just postulated these. And it turns out they're pretty accurate. It's pretty amazing. Number one, each element is composed of extremely small particles that they call atoms, okay? And that one turned out to be true, right? So we have those little tiny things called atom. An atom of oxygen, or an atom of the element oxygen, and the atom of nitrogen, and so they look different, and they are different. All atoms of a given element are identical, but the atoms of one element are different from the atoms of all the other elements. Well, that turned out to be true as well. It's kind of nice, so he's 2 for 2. Okay, so that's the second postulate. Third postulate was atoms of one element cannot be changed into atoms in a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. And that's true in his day and age, and it's true in the way we do chemistry. But we do know now through particle acceleration that we can make larger atoms out of other atoms. We can bombard, let's say, something like a plutonium with some helium, and we can build bigger atoms, which we will see when we get to nuclear. But for the most part, that is consistent. That is true. All right, we use that. And you have to remember what was going on in Dalton's day. You still had a lot of these alchemists, and what were alchemists trying to do? Turn things into other things, right? I mean, this thing is worth a lot of money, and this thing is not worth very much. So maybe I can take something silver and figure out how I can take something gold and yellow and make it gold. And there's a lot of sincere chemistry, by the way, but people that really thought I can take this yellow sulfur and this liquid mercury, and somehow, if I get the right ratio, if I get the right temperature, the right pressure, the right something, I can make gold. And I can become a gazillionaire through chemistry. Okay? The alchemists very sincere, and actually we know a lot of chemistry from a lot of their trial and error, by the way. Okay? They were very sincere in what they were trying to do in the original alchemist day. A lot of our metals, a lot of our are metals that have lots of other compounds in them. What makes stainless steel stainless steel? Why is stainless steel so amazing? Why is it stainless? Well, because you put some carbon in with iron, turns out, a little boron in there too, and you can begin to work with the properties of iron to make it not so susceptible to oxidation. All right, so again, postulate number 3, turned out, he's right. Postulate number 4, compounds are formed when atoms of more than one element combined, a given compound always has the same relative number and kind of atoms. And he was correct. So you have to remember, this is like before, when we still have horse-drawn carriages and wagons, when he's in a laboratory with a candle working through his chemistry. It's not like he had a modern lab. So he was just working with Bunsen burners and flames and glassware under candle power, candlelight. So that he came up with these things from his studies is actually pretty remarkable. So that's why he's really considered the father of the atomic model, even though we do call it the Bohr model, because Bohr really resolved a few of the quantum issues that we had with it. So again, that's the Dalton postulate. Now, one of the most amazing things, this final one here, this law of multiple proportions. If two elements, A and B, form more than one compound, the masses of B that combine with a given mass of A are in the ratio of a small whole number, basically an integer. And that was really important to establish that. And we now know that as the mole ratio, the stoichiometry ratio, but that's a very important thing, and that's because of, again, the ratio 1 to 1 is going to be 1 to 2, and you look at the masses of this, and again, 2 to 1, again, the mass, 28 to 16, those are their atomic mass units, which we haven't really talked about yet. And you can see that this ratio really does hold up, and that was really this law of multiple proportions that Dalton postulated. Okay, really, really amazing foundation for understanding of how we do chemistry today, and not much has changed from those original postulates at the turn of the 18th century. Okay, kind of cool. Okay, so from Dalton's view, now we need to jump down into what is an atom. And how would we figure out what an atom is if we can't look at it under the microscope? So a couple different tools were used, a couple different tools were invented and discovered, or invented, I should say, and then used. Because remember, sometimes we have to actually develop the apparatus that we're going to use to do the experiment. That's probably one of the fun parts of it, if you're more like the physics mind of chemistry, to actually come up with a machine that does the testing, that does the imaging. Today we use what's called nuclear magnetic resonance if we want to see the ratio between hydrogens and carbons in the human body. In the hospital, it's called the MRI, magnetic resonance imagery. It came out of the chemistry lab. Chemists stole it from the physicists. The physicists built it to look at the carbon-hydrogen ratio, to look at the hydrogens and carbon-13 interactions. Amazing stuff. Chemists stole it. We use it to look at our molecules. And we can tell, those of you that will take what I call elucidation course, you can actually come up with the amazing, beautiful arrangement of the molecules through peaks on an NMR. What's funny about the NMR, it's actually in the chemistry lab, ours is in the lab over there, it's called the nuclear magnetic resonance imagery. Okay? Nuclear magnetic, it's called NMR. But here's what happens. The public doesn't understand it has nothing to do with nuclear. There's no nuclear chemistry going on in an NMR. It's because it's looking at the nucleus, or the proton of the nucleus. So they call it nuclear magnetic resonance. So the resonance, these little tiny magnets, have a certain frequency that they resonate at. But because they were going to start putting people in these big machines, they hacked off the N and they just called it the MRI, magnetic resonance imagery. It's the same technique. We just look at molecules. We put molecules in these machines in a magnet, and an MRI puts the body inside the magnet. So it's kind of cool technology. And again, we'll build on that. So we need to figure out what atoms are made out of. So one of the first tools was to work with the electrons. What's going on with these electrons? Because remember, most of the chemistry that we do in here is the movement of electrons. So a lot of work was done first to figure out and kind of look at what are electrons. And this wasn't really resolved until early 1900s when we got to the Schrodinger equation, and when Einstein and Oppenheimer and Bohr were really working on this, and we'll talk about that a little bit. So here's J.J. Thomson, not here, but this is the era with which we're talking. This is about the turn of the 19th century. Is it 19th century? Yeah, turn of the 19th century. And this is about the technology of automobiles and the time that this chemistry was going on. So again, here is what Thomson was doing in the laboratory. Simultaneously, here's what was going on outside the laboratory. So we're this era of discovery, both for our technology and the evolution of the automobile, and our understanding of basic concepts of the electron. And so one of the very first things was Thomas made these things called cathode ray tubes. And what you do is you put a gas inside there, and you put a charge across it, and you can see that if you take a magnet, you can get the beam. And some of you have probably played with these in lab. I think physics lab has a couple of these. And we can play with them. They're kind of cool. But you put a charge across there, you put a big strong magnet, and you can get the beams actually to move. And of course, most of you will know this is the original television technology. This is how we got. This is how we had an image on a tube, on a phosphorus tube, where the electron slammed into it and lit it up. And then if you can control that, you can design an image. Nowadays, it's very rare to find a tube TV. Most of them are LED and LCD and all these OLEDs and QLEDs and super QLED, all these things like that. But really what's happening there with the old school TVs was we were just slamming electrons into a screen that had a coating on it that was fluorescent, and it would light up. And if you ever YouTube some of the original, the very first TVs, very crude, but you can see an image of a person, and again, it's very crude, but they were there. And from that technology to where we are today is just absolutely incredible. But again, that was some of our very first understanding of electrons by passing a charge over it here, shooting it down a flight tube, and then putting a magnet, and we can aim that electron beam somewhere. But here's the key: the electron beam was susceptible to a magnetic charge, meaning the beam itself had to be magnetic. Okay? And they discovered, oh, it's the electron, it's the negative side. It's attracted to the anode side, which means that it itself is negative, so the electrons are negative. Okay? So we now know that. We also know that the charge to mass ratio from the original work of Thomas is 1.76 times 10 to the 8 coulombs per gram. Now here's what's really cool. If we can figure out how many coulombs what the charge is, or how many grams what the weight is, we can figure out the other one. Does that make sense? Since we know the ratio, if I can figure out the charge of the electron, then I can figure out the mass of the electron. Or if I can figure out the mass of the electron, I can figure out the charge. Well, which one's easier? Well, history looks at it and says, let's figure out the charge, because that's a little bit easier. Now, here's the cool thing. I want you to think about it. I think I have an actual video, not the real thing, but of this experiment. What's really cool about this, how would you figure out the charge of an electron? It's really interesting. I wouldn't have thought of this one, but what if we could suspend? What if we could suspend an electron? What if we could make an electron go down and then levitate the electron if we could make it a charge? And that's exactly what happened with the Millikan experiment. So the Millikan oil drop experiment is one of those fascinating ones, where they had a charge across a gradient here. Okay, they took an oil dropper. It was actually a perfume. What was it called? Infuser, whatever the perfume things, that the old school perfume things that you squeeze and then it puffed out. And they put oil in that to put it in a very fine mist. Once the oil was charged, okay, it would fall down through this hole. And if you knew the charge that you put across here, as you turn the voltage up, the charged particles eventually are going to levitate between the two poles. And at the point with which they're levitating is the charge equal to the charge across the two plates. That's ingenious to me that this is how this was done in 1909. And here's the thing. By doing this over and over and over and over and over again, they were able to determine, oh, do I not have it? Ah, stink. I used to have it on this one. But anyway, they were able to determine the charge of the electron, and they had it down to about 100th place, and they were really close to what we know it to be today. We just have it down to about the 10,000th place today. But up to the 100th place, it was spot on. It's pretty cool. That's the crudeness in 1909 of the electron and the electron's charge. So from that, if we know the mass, the charge to mass ratio, we know the charge, now we know the mass of the electron. And so that's how we came up with what we have today tabulated as the actual mass of the electron. Okay? Now, Rutherford worked with radiation in a way that he took little streams of radioactive beams, and he also took it across an electrically charged plate, and we came up with alpha, beta, and gamma. Now, we're going to come back to radioactivity in chapter 21, so I'm not going to talk about it that much here. We will explore this in its fullness. But just know that was happening about the same time that a lot of this other stuff. We now know the electron. Let's move into the nucleus and and see some of the history of how the nucleus was fleshed out. The original model, circa 1900, which was incorrect, so science by its very nature, remember I talked about science is in the process of change. So if you'll remember, you might not, but any theory, you can propose a theory, and you say, okay, I'm seeing some information with my apparatus, so I'm going to propose a theory. But what happens when you start to have anomalies, okay? And what we're going to see is a massive anomaly. And I think this to me is one of the important parts of this lecture. Anytime we see an anomaly in a scientific model, we should focus in on the anomaly. Because more discovery, more science has been found through following the anomalies, leading to brand new windows of discovery. Okay? In fact, one of the most amazing ones, if you want to talk about are organisms getting more complex, or are they getting less complex? Because one theory says that we're getting more complex. We go from bacteria to the next one up, to the next one up, to the next one up, to the next one, finally to a human. But Scott Minnick, out of University of Idaho, he had thought about some of these killer bacteria that get on our skin, like MRSA and those type. And he said, I wonder why these things are so deadly. And so when he did the sequence of its DNA, he realized that these killer bugs actually have lost information that causes them to naturally be dealt with. And he sequenced the missing components, put it back in, and they became completely harmless again. So they haven't gained new information to become killer, they've lost information to become killer. So it's not getting more complex, it's actually going the other way. Very fast, and it opened up a brand new area in biology discovery through that one assumption of, wait a minute, what if? And so same thing here, this wasn't the right model. What happened was J.J. Thomas said that, well, basically what happens is we call this the plum pudding model because there's this overall positive kind of sphere with electrons buzzing around in it, all right? So let's come up with an experiment to confirm that. If that's the model, that's the theory, can I come up with an experiment to either confirm it or deny it? It is falsifiable, right? So I can go to the lab and I can attempt to falsify it. So again, this is one of those amazing, to me, how you would come up with a way to either falsify or discredit this theory. And it was really Ernst Rutherford's gold foil experiment. This one's fascinating to me. And here's why it's fascinating to me. What Rutherford did was he was able to, because gold is super malleable, you can get it down to just a few atoms thick. That's how thin you can get it. Just a few atoms stacked on top of each other. That's how you keep pounding it until it gets that thin. You actually pound it so thin you can actually put it on food and eat it. So he made this really thin, super thin foil. And he shot alpha particles at it. Because here's the thing. If this is the plum pudding, and this is the nucleus, and these are really small particles, the alpha particles should just go right on through, just blast on through. And so, for the most part, as he's shining these alpha particles through the gold foil, most of them are ripping right on through the foil like you would expect. But here's what happened. Every once in a while, there was a mass anomaly. Mass anomaly where one of the particles would be deflected at a really high angle. And that caused him to say, no, this model is not correct. There's something really big inside these gold atoms that's causing the alpha particles to be blasted back. All right? Again, it was an anomaly. So in this model, the Rutherford model, there was a massive anomaly from the model. Okay? And so because of that, there was a paradigm shift in our understanding, our theory, our belief of what atoms look like. I'm going to show you this one. This one's actually, they actually went back and reconstructed this. If I have, I might have it on this hard drive, but if I do, and if not, I'll play it on Monday or on Wednesday. It's worth watching if I can find it. I just don't know if I can find it. Hang on a second. No, I don't have it. I'm gonna try. It's just on a different hard drive. I will bring this in. I'll start class on Wednesday with showing you because it's really cool. Showing you a reconstruction, an actual apparatus. I think they did it in England. where they actually redid his apparatus to just show how cool this, and to me, what an amazing discovery that is. So from this experiment, okay, as we're building on this, now we understand the electron. This helped us understand the nucleus of the proton and the neutron. And so again, if this model would have been correct, the plum pudding model would have been correct, they would just keep on going through. But because of this real strong deflection on just a few, not many, but a few, it meant that this nucleus was really small but really dense. And so that's where the current theory that the nucleus holds the density or the most mass in the nucleus is from the neutrons and the protons. So our current model comes from that Rutherford experiment. One of the other things to keep note of, oftentimes when we look at the atom, well, you might ask yourself the question, how do we know the actual size of atoms? And typically what's done is we look at two atoms together and we take half of the ratio of the distance between two of those to come up with the radius of the atom. And we'll get to that when we get to atomic size in the next subsequent chapters. But this is our current theory of the atom. This is incorrect. Sometimes you see this cartoon for an atom. It doesn't work that way. It's funny that that's the accepted symbol for the atom, but it's not the right symbol for the atom. And the reason for that is the electrons are not in orbit around the nucleus. Do we know why? What would happen if they were in orbit around the nucleus? They're not in orbit like the moon's in orbit around the Earth. You notice that? You know that every time the moon goes around the Earth, what's happening? It's actually being sucked in. Not much, but it's coming closer towards us every time it goes around. Okay? So if an electron, every time it goes around the nucleus, is moving into the nucleus, what's happening? Eventually it's going to collapse, or you're not conserving energy. Energy has to be conserved. So electrons don't buzz around. Electrons are in energy levels. It's the weirdest thing. It's called quantization. We will get to it. Okay? The universe is digital, not analog, and I'll explain that. But that is not the one. That assumes it's an analog universe. It's not. The universe is a digital universe. Ones and zeros, not. Anyway, we'll get there when we get to quantum. It's super cool. You'll love it. So our current theory, the Bohr understanding, is that there's the nucleus and then electrons in what we call energy levels. Principal quantum number 1, 2, 3, 4, etc. as we get larger in electrons, and we will get that. Some of you might know that as 1s2, 2s2, 2p2 if you've had chemistry before. The electron configuration. Those are their energy levels or their energy shells, and we will work on that quite a bit in here to have a good foundation. But they're in energy levels. So if I'm looking at something like helium here, actually that looks like that's beryllium. Looking at something like beryllium here, 2 of the electrons are in what we call the 1s shell, and the other 2 electrons are in the 2s shell. And we'll get to that and we'll build on that. But this is the current theory, the current understanding of the atom. Is it correct? May or may not be. There are other theories than the Bohr model. This one requires quantum mechanics to explain it. It's the accepted theory. So scientists work on the accepted theory. There is another theory out there, and it looks like this. It's called the Lucas model, and it's the spinning rings. It's a fascinating model. If you have time, Google it, because it's worth reading. It doesn't need quantum mechanics. It's a very fascinating theory to me. And it basically says that no, the electrons are little spinning rings clustered around these levels. So just a different theory, and it's been around for a while, by the way. It's not something new, but there are other theories out there of the atom. This is the one we accept today. This one's not right. This is what we accept to be correct. Okay? So here's what you need to know. You don't have to memorize this, but here's what we know today. The electron is the negative charge, and it has a really small mass of 5.486 times 10 to the minus 4 atomic mass units. Protons and neutrons. You should know which one's heavier and which one's not and why. It's not very difficult, but the neutron, if you'll notice, is heavier than the proton. Okay? This neutron is heavier than the proton. And here's what you're going to learn in nuclear. It's because if the neutron loses an electron, it becomes a proton. Now that's weird, it should bug you. But if you look at that, this and this make this. Positive and negative make neutral. Okay? So protons are lighter than neutrons. Neutrons are the heaviest part of the nucleus. And again, we'll break that down when we get into it, but for now, that's what we'll leave it. These are the accepted weights today that we have for both the neutron and the proton and the electron. Okay. Now, what's fascinating about this is when you look at this atomic mass scale, they're really, really small, of course. And so when we see this, we basically use what we call the atomic mass unit. One atomic mass unit equals 1.66 times 10 to the minus 24 grams. That's a really, 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 really small number. And that's been calibrated or standardized against a special isotope of carbon. It's carbon-12. All right, carbon is really special. Carbon-12 has 6 protons and 6 neutrons. And it has a weight of exactly 12.000000000 atomic mass units. And that's what the mass has been calibrated against or standardized. So the entire periodic table is standardized around carbon-12. And you'll notice carbon is not 12.011. So we have to take into account the 1.11% carbon-13, a little bit of carbon-14. There's actually a little bit of carbon-11 too floating around. All right, but this is what we use, atomic mass units. Again, if you've had chemistry, you know that atomic mass units quickly moves over into grams if we're talking about the mole, okay? Which again, we will build on. So these numbers up here are either atomic mass units or grams per mole. Same thing. Okay, same number. Not same thing, same number. All right? Okay, and so here's what I was talking about. Compared, all masses of atoms are compared to the carbon atom that has 6 protons and 6 neutrons, or the carbon-12 that we know. And we can actually send these things down a flight tube. We do this all the time in our advanced lab. We have a mass spectrometer in there that has a flight tube in it. We run molecules through it. We blast them. It's like shooting with a shotgun. And it just fragments them as they're coming through that flight tube. And those fragments have different atomic mass units. And so you can see a pattern of fragmentation. So if you constantly are shooting cocaine in this machine, it's blasting them apart. It has a really unique profile. Right? You shoot something else in there, some other medicine or some other molecule, it's going to have a different fragment pattern as you blast it apart. And that's how we can detect and analyze blood samples or other samples and know that because we know the fragmentation pattern of those molecules through a flight tube. But again, we use that atomic mass units and we standardize that with carbon-12. Okay, kind of cool, right? So I'm gonna add to this. There are 4 locations. There are 4 locations on an atomic symbol, not 2 like this graph shows. Those are the 2 important ones for now. But let's say we have carbon. Let's not use carbon. Let's just use a big old giant X. Okay, there are 4 locations around this symbol. All of them are absolutely important because we're going to build on this as the semester builds. The very first 2 that we're going to see are here. You have your mass number and your atomic number. So you can see here our atomic number is the blue number up on our periodic table. The atomic number from our very first lecture talking about how chemistry is not very complex, or I should say that, it's not very difficult because we're really just counting from 1 to 118. We just say funny things like carbon for 6 protons, 6 electrons. We say nitrogen for 7, we say oxygen for 8. But again, all of that is dealing with the blue number up here. Bromine happens to be 35, carbon being 6. So those are, as you can see here, those are the atomic numbers. The atom, what is the atom assigned? How many protons does the atom have? 1 through 118 are our choices. So with that, the atomic symbol, the atomic number goes here. So this is the atomic. All right? Up here, as you can see from here, is my mass number. All right? So something like carbon-12, if carbon-12 has 6 protons and 6 neutrons and 6 electrons, I know what it weighs because I just showed you the table of how much these things weigh in atomic mass units. So I can come up with the weight of this thing. And carbon-12, being standardized, is exactly 12 atomic mass units. Okay? So that's my atomic, or my mass number. Roughly, not exactly, but the average of these atoms in the crust of the Earth and our foreseeable universe, or solar system, is this number here. Okay, this is the average of those. And as we build this, you'll see that, oh, okay, that's where isotopes. We'll get into isotopes in this as well. all right? So that's the symbol. That's the atomic number, mass number. Now, here's the other two sides of the symbol. This, what do you think this one is going to be? I'm going to take a stab at it, the chemistry? So I'm just not flapping my gums for 45 minutes, 50 minutes? No? Okay, this is the charge of the atom if it becomes an ion. So we're going to see real quickly here that if you're over here on this left side and you're sodium, remember, neon sits right here, not over there, over here. Neon sits right here. So sodium says, if I just lose one electron, I mimic nobility. So sodium is going to prefer to put a +1 up in that upper charged box. If you're over here and you're chlorine, you're like, man, if I could just get one electron, I mimic nobility. And I'll explain why nobility is nobility. So what do you think the charge is going to be up in that box? -1. Oxygen says, man, if I could just grab 2 electrons, I mimic nobility. Therefore, oxygen is going to be 2-. Okay? And become an anion. So that's why everything over here on the left of nobility wants to become an anion, wants to gain electrons. With the noble gases again right here, everything on the right side of the noble gases wants to lose electrons to mimic nobility. So +1, +2, again 2 and 3, and 1 and 2 and 3 of all these of transition elements. Okay? So again, that's the charge. And finally here, goes back to your Dalton, and this is going to be your stoichiometry. Your stoichiometry ratio. So when you have a hydrogen, you have 2 of those, so it becomes the stoichiometric ratio, telling me that I've got 2 of those that make up this compound. But there, so all 4 of these positions around our symbols becomes very important. Okay? Atomic number, that defines the atom. Mass number tells me the weight of the atom. Charge tells me if it's an anion or a cation. And then finally, how many of those to make up this compound. Cool? So those are your 4 locations around the atomic, and that's how we typically work in a chemistry setting. Okay? All right. Yeah. Okay, so isotopes are same atomic number, different mass number. So they have the same number of protons throughout. So that's why it's going to be consistently carbon. So carbon, I know because it's carbon, this has to always be 6. Okay? And this is going to be 6, at least in its electron configuration in its ground state. Now this is what we're going to spend a lot of time understanding how atoms like to lose and gain electrons, and they don't share nicely. Some really don't share nicely at all. Oxygen is the biggest narcissist. Well, fluorine's the biggest narcissist on the periodic table, but oxygen is right there with it. This is what's changing in an isotope. So an isotope changes the number of neutrons. Not all atoms have neutrons. Hydrogen does not have a neutron. Hydrogen is 1 proton and 1 electron. But hydrogen has 2 bigger brothers. So you have hydrogen, 1, 1. You have hydrogen, 1, 2. And you have hydrogen, 1, 3. Okay? This is called hydrogen. This is called deuterium. And this is called tritium. If you've ever watched any of the Manhattan Project or any of the research and the incredible amount of work that went into splitting the atom, in order to do so, it really required what they call heavy water. Some of you might have heard that term, and that's T2O. A very, very rare isotope of hydrogen. Deuterium is pretty common. We use this a lot in the organic lab. So like D2O, we have deuterated water, we have deuterated solvents, because deuterium is invisible in the NMR because its nucleus is paired up, so it's not observed in a magnetic field. Whereas hydrogen is visible in a magnetic field because it has an electron and a proton. All right, kind of an interesting thing, but we'll get into that a little bit later. But T2O was really important during the discovery of splitting atoms and some of the research that went into that, and figure out how you even make T2O in the first place. But it's kind of a neat subtopic, and if we have time in chapter 21, we'll look into a little bit. It's pretty cool. Okay, so the atomic weight, okay, is different than the mass number, and that's because of the isotopic ratio. So the way that we actually get the numbers up here on the board, right here, 12.011,